In this video, we continue with Chapter 4 on linear models and matrix algebra, specifically looking at matrix operation. First, addition and subtraction. Second, scalar multiplication, matrix multiplication, division, and the sum notation. So first, addition and subtraction of matrices. In order to be able to add or subtract two matrices, we have to have the same dimension. What does this mean? It has to have m times n rows for both matrices. And remember, what is an element of a matrix? It is simply an entry like A11. So, for example, if we have two matrices, 1, 2, 3, 4, this is a 2 by 2 matrix. This is equal to the matrix 1, 2, 3, 4, but it is not equal to the matrix 3, 4, 2, 1. Therefore, for a matrix to be equal to another matrix, each element must be exactly the same. We can do the same for larger matrices, so 1, 2, 4, 4, 0, 6, 8, 2, 1, which is a 3 by 3 matrix. This is not equal to 1, 2, 4, 4, 1, 6, 8, 2, 2. Why? We have two elements that are not equal to each other. Okay, so for addition and subtraction, you can only add or subtract when it's the same dimension. And when you add or subtract a matrix with the same dimension, you simply add or subtract the same element from the second variable, from the second matrix. So for example, if we have matrix A equal to 1, 4, 6, 8, 2, 1, 0, 4, 3. This is a 3 by 3 matrix. And we have matrix B equal to 4, 6, 8, 1, 2, 3, 1, 0, 1. What is A plus B equal to? We add each exact entry to each other. Can we do this? First, check our dimensions. A is a 3 by 3 matrix. B is a 3 by 3 matrix. So we can add A plus B. So 1 plus 4 is our first entry. So that would be 5. Second entry, 4 plus 6, which is 10. Third entry, 6 plus 8, which is 14. Second row, first entry is 8 plus 1 is 9. Second row, second entry is 2 plus 4. 2 plus 2 is 4. Third entry, second row, 1 plus 3 is 4. Third row, first entry, 1 plus 0 is 1. 4 plus 0 is 4. And 3 plus 1 is our final entry, so 4. So this would be A plus B And as you can see, for addition or subtraction of matrices, you end up with the same dimension as your original matrices. What does this look like in a more general form? A11, A1. So a general form would be where we only have unknowns in our matrix. So if we have A11, A12, A13, A21, A22, A23, A31, A32, A33, plus, for example, B11, B12, B13, let me just fix this B, B21, B22, B23, B31, B32, B33. This would be equal to, the first entry would be A11 plus B11. This is one entry. So if we have two unknowns added together, it's one entry. The second entry is A12 plus second entry B12. Third entry A13 plus B13. Second row A21 plus B21, A22 plus B22, A23 plus B23. Final row A31 plus B31, A32 plus B32, second entry, and final entry A33 plus B33. And you can expand this to an m by n matrix. Second, we have scalar multiplication. A scalar, in matrix terminology, is simply a number. Okay. So for example, if we take our general A matrix, A11, A12, A13, A21, A22, A23, A31, A32, A33, and we multiply this by the scalar b, so in this case b is only a number. For scalar multiplication, you multiply the scalar, in our example b, with each element in the matrix. So what you end up with is BA11, BA12, BA13. Second row, BA21, BA22, BA23. Final row, BA31, BA32, BA33. If we do a numeric example, for example, a scalar 2 times the matrix 1, 0, 4, 4, 1, 1, 2, 3, 0. Multiplying the scalar with this would be 2 times 1 is 2, 2 times 0 is 4, 2 times 4 is 8. Or 2 times 4 is 8, 2 times 1 is 2, 2 times 1 is 2. Third row, 2 times 2 is 4, 2 times 3 is 6, and 2 times 0 is 0. So that is scalar multiplication. Finally, or thirdly, we have matrix multiplication. In which we have a lead matrix, which is the first matrix, and we have a lag matrix, which is the second matrix. This is important because for matrix multiplication, we have a conformability condition. This means the lead column must be equal to the lag row. Okay, so for example, we have to check our conformability condition always. So this is important that we check this. So let's do an example. We have A equal to 1, 0, 4, 2, 1, 1, and 3, 1, 3, 4, 1. And we have B equal to 4, 1, 1, 0, 2, 1, and 2, 1, 0. So what are the dimensions of matrix A? Matrix A has 1, 2, 3 rows and 1, 2, 3 columns. So matrix A is a 3 by 3 matrix. What's the dimension of matrix B? 1, 2, 3 rows, 1, 2, 3 columns. So matrix B is 3 by 3. So first, if we want A times B, we need to check the conformability index. So is the lead, which is A, column, which is 3, equal to the lag matrix B, row, is 3. So what I do is I write it down, 3 by 3, underneath what I want, and you can simply check those two. So yes, we can multiply A times B. So how would we multiply A times B? So I'm just writing down the numbers or the matrices from above. Now what we do is we take row 1 of A and we multiply it by column 1 of B for the first entry. So that would be 1 times 4, 1 times 4, plus 0 times 0, plus 4 times 2. Second, we take row 1 times column 2, which would be 1 times 1 plus 0 times 2 plus 4 times 1. And then finally, we take row 1, column 3, which is 1 times 1 plus 0 times 1 plus 4 times 0. I'm just running out of space here. And you do the same for the other rows. So you end up with row 2 is 2 times 4 plus 1 times 0 plus 1 times 2. Row 2, column 2 is 2 times 1 plus 1 times 2 plus 1 times 1. Row 2, column 3 is 2 times 1 plus 1 times 1 plus 1 times 0. Final row, so row 3, column 1 is 3 times 4 plus 4 times 0 plus 1 times 2. Third row, second column is 3 times 1 plus 4 times 2 plus 1 times 1. Finally, third row, third column, 3 times 1 plus 4 times 1 plus 1 times 0. If we then calculate this, it is 12, 5, 1, 10, 5, 3, 14, 12, and 7. So again, first check the conformability condition with matrix algebra. Is the column of the lead matrix equal to the row of the lag matrix? In this case, 3 by 3, so yes, it's conformable. What you do then is you take row 1 of the lead matrix and you multiply each entry of row 1 with the same corresponding entry in column 1. And you add the second element of row 1 to the second, multiplied by the second entry of column 1 to the addition of entry 1, row 1, and column 1. Let's do another example. In this case, matrix A equal to A11, A12, A13, our general matrix, A21, A22, A23, A31, A32, A33, close, and B matrix, B11, B12, B21, B22, B31, B2, B32. Let me just write this neatly. B31, B32. So first, matrix A and B. Matrix A is a 3 by 3 matrix. Matrix B is a 1, 2, 3 rows, 1, 2 columns. So it is a 3 by 2 matrix. Conformability, A's number of columns is equal to B's number of rows. So yes, we can multiply A and B, and AB would be equal to a 3 by 2 matrix. So A times B. So we take entry 1. So we take row 1 times column 1. So it would be A11, B11 plus A12, B21 plus A13 B31. I'm just going to rewrite this to make more space. So AB is going to be a 3 by 2 matrix. So row 1, column 1 would be A11 B11 plus A12 B21 plus A13 B31. Row 1, column 2 is A11 B12 plus A12 B22 plus A13 B32. Then we have row 2, column 1 is A21 B11 plus A22 B21 plus A23 B31. Row 2, column 2 is A21 B12 plus A22 B22 plus A23 B32. Row 3, column 1, A31 B11 plus A32 B21 plus A33 B31. And finally, row 3, column 2, A31 B12 plus A32 B22 plus A33 B32. What do we end up with? 1, 2, 3 rows by 1, 2 columns. The question of division. And the answer is we cannot divide matrices. The simple answer to this is because of this conformability condition. What we can do, which is a similar concept to division, is we can find the inverse of a matrix, which we will do later in this chapter or in chapter 5. Finally, we have the sum notation, which is simply the capital sigma of the Greek alphabet. So for example, if we have A11 plus A12 plus A13, we see that we have A1, 1, 1, and then it adds a step to the second part. 1, 2, 3. If we want to write this into sum notation, we can write it as A. 1 remains the same in all 3 steps, but our second element adds a step to each addition. So j would be equal to 1 because we start counting at 1 and we count up to 3. Because we have this A11B11 plus A12B21 plus A13B31, it's useful to write this in a simpler form of summation. So for example, if we take A11B11 plus A12B21 plus A13B31, which is our first entry in AB, we can write this as the sum if I is equal to 1 up to 3. We have A1, 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 2, 3. So A1I. B is our second element. We have 1, 2, 3. So this would be I and then 1. So it is a much shorter form than writing A11 plus B11 plus A12. Instead, we can simply say the sum of A1 I B I 1 over I equal to 1, 2, 3. So if we were to write AB as matrix C in sum notation, it would be equal to the sum of I equal to 1, 3 of A1J. Let's make it J so it's more clearer and not confusing with 1. BJ1. The sum of J equal to 1 to 3 of A1J, BJ2. Second row would be equal to the sum of J equal to 1 up to 3 of A2J, BJ1. Second entry would be J, the sum equal J equal to 1 up to 3 of A2J, BJ2. And final row would be sum of J equal to 1 over 3 A3J, BJ1. Sum of J equal to 1 over 3 of A3J, BJ2. Another thing to note, remember A was our lead matrix. So our lead matrix makes the rows. So you'll see it's A1, 2, 3. A1, 2, 3. B was our lag matrix. So B changes per column. So you'll see it's B1, 1, 1. And then B2, 2, 2.